to be given by Anton, who's going to tell us something about how to bridge the gap between our high-level languages and our hardware weak memory models.
Can you hear me now? Okay. Hello. Thank you for introduction, Scott. First of all, I guess we all agree that the title is rather long. So let me shorten it a bit by replacing programming languages and memory models with acronyms. Okay, good. Now at least it fits on one line. Let's talk it through. So first of all, we all know that there is a gap between programming languages and hardware. And the usual bridge for that gap is a compiler. And in the context of this work, we are interested in correctness of compilation. So what does it mean for a compiler to be correct? Actually, it means that for all behaviors which are allowed for for a compiled program on a target hardware, they are also allowed for source program in programming language semantics. So the last part is memory models, and actually, in context of this work, memory model is just a fancy term which means semantics of programming language or hardware with concurrency. And to understand what it means for a memory model to be weak, let's consider an example which is a bit, looks like an example which was in Azalea's talk, but a bit reversed, because here we have two threads, and in each thread we first have a read instruction and then a write instruction. There is also a data dependency in the right thread, and we assume that both locations x and y are initialized by 0. If one asks me to introduce himself to concurrency, I usually say that, okay, suppose in every thread we have a program counter, and at each step of program execution, a scheduler decides which thread executes an instruction. And in this case, consider that the left thread executed first instruction first. So this is how we got a equals 0. Then the left thread can continue and write 1 to y. After that, the right thread might be executed. So this is how we get a equals 0, b equals 1 for this program. So the memory model or semantics which I just presented is a strong memory model. It's also known as sequential consistency. And obviously, for that program in sequential consistency, it's impossible to get a result a equals b equals 1. However, it's possible to get such a result if you execute this program on modern CPUs like ARM and Power architectures. And it is due to different optimizations which CPU does during execution of program. So behaviors which cannot be explained by sequential consistency are called weak behaviors, and memory models which allow weak behaviors are called weak memory models. So there are many memory models out there. Here I listed memory models which are considered in our paper. So on the right-hand side, we have hardware memory models. On the left-hand side, we have programming language memory models. So there is a well-known C11 memory model, and it's also well known that this model has a problem related to so-called out-of-thin-air values. So there are some attempts to solve that problem, among them the promising semantics, or just promise, and RC11, which stands for repaired C11. So there are many compilation correctness arguments in the literature between these memory models. Some of them are verified in Kang, some of them just pen and paper proofs, and as pen and paper proofs, they are error prone. And actually, we found a mistake in an argument of correctness of compilation from promising semantics to power. Also, it used to be considered that a correctness compilation scheme, standard compilation scheme from promising semantics to ARM v8.3 is correct. However, we found out that for RMWs it has to be strengthened a bit. So this is the state of the art, and as you see, not all errors are there. Also, the whole picture is not scalable in the sense that if one introduces a new programming language memory model, she has to prove a lot of compilation results about it. Next, I'm going to present what we did in our paper. So first of all, we introduced a new memory model, IMM, which stands for Intermediate Memory Model. We proved that it's an abstraction for all mentioned hardware memory models. We showed correctness of compilation from listed programming language memory models to this IMM, and via transitivity, we got all possible correctness of compilation results in this diagram. So let me say a couple of words about the model itself. So first of all, it's declarative, as all mentioned hardware memory models. And declarative memory model means that semantics of a program in this model is a set of graphs, and each graph represents some specific execution of program. Here, first two graphs represent sequential consistent executions, and the third one represents a weak execution. And in these executions, vertices are different memory accesses like reads and writes, and edges are different relations among these accesses. Like here we have PO, which stands for program order, and RF, which stands for reads from. We also have a data dependency here. So declarative memory models are also often called axiomatic memory models because they use axioms to forbid some behaviors. And one of the simplified versions of an axiom used in IMM says that a relation data union relation RF should be acyclic. So as we see, there are no cycles which uses only RF and data ages. So that is why this behavior is allowed by IMM for this program. So getting back to our picture, IMM somehow shortens the gap between programming language and hardware memory models because it's a blend of ideas from both groups. So for example, IMM preserves syntactic dependencies as hardware memory model do. Also, it uses C11 style coherence axiom as PL memory models do. Also, the model itself is non-multi-copy atomic as it's an abstraction over ARMv7 and power architectures, unlike ARMv 8.3. However, unlike ARMv7 and power architectures, the definition of IMM is quite simple comparing to them. Okay, as I said, we use IMM as a central piece of our correctness of compilation results. All of these results are proved in Kang. The whole development is around 30,000 lines of code. Actually, the most complicated part here was the correctness of compilation from promising semantics to IMM due to different representation style of these models. So let me explain a bit this compilation correctness result. And before I'll continue there, I'll explain how one can get a weak behavior in promising semantics. So promising semantics is also an operational memory model as sequential consistent memory model, and it also uses program counters. So to get a weak behavior which ends with A equals B equals 1 for that program, the left thread should start with promising to write 1 to Y. After that, the right thread may read from this promise. So this is somehow a mechanism for out-of-order execution of writes in promising semantics. However, not arbitrary promises can be made. So the promising semantics require threads to certify its promises, and certification here is done by executing thread in isolation and showing that the thread can fulfill its promises in this isolated execution. So that is why the right thread here cannot start execution of the program by promising writing 1 to X because it has to read 1 before that. Okay, so after the left thread promised to write 1 to Y, the right thread can read from this promise, and then to write 1 to X, and this might be read by the left thread afterwards. So then the last step is to fulfill the promise. So this is how one can get A equals B equals 1 in the promise in semantics. So getting back to correctness of compilation from promise in semantics to IMM, usually such results are proved via simulation. However, in this case, it's not perfectly clear how to apply simulation right away because it's unclear how to simulate graphs because they are solid structures. So to solve that problem, we introduced an operational semantics of traversal for IMM executions, and we define it in such a way that promise in semantics can simulate such traversal. So here we have some intermediate state of the promise in semantics of executing that program, and we have some traversal configuration. Traversal configuration consists of 2 sets, covered and issued ones, and issued events, they correspond to writes being promised by promise machine, and covered events correspond to instructions which are normally executed by promise semantics. So the overall structure of the proof is following. First, we introduce the operational semantics of traversal. Then we show that this traversal is complete in a sense that there is a traversal which covers all events in the graph and issues all writes in the graph. And then we show simulation. Simulation might be represented as 2 theorems. First, we show that initial state of traversal and the promise in semantics are related via simulation relation. And then we show that if there is a traversal state which is simulated by a promise semantic state, and there is a step in traversal, then it might be simulated by promise semantics. Actually, the most complicated part in this theorem was to show that there is exactly such promise prime which might be reachable from promise, not to relate it with traversal prime, and actually it's due to certification, which I mentioned before. I'm not going to say much about this problem here, but actually we use so-called certification graphs. So we, to do this step, we at every step of simulation we construct certification graph from current traversal configuration and IMM execution, and then we do simulation of this traversal graph to get a certificate for promise semantics. So let me show you the whole traversal of this program, of this execution, and corresponding steps which promise semantics takes to simulate this traversal. So first of all, here we can either cover some step or issue some step, I mean in general in traversal, but here the only thing which we can do in the beginning is to promise this write. And it's due to the fact that reads cannot be covered until the corresponding writes are issued. So, that is why we have to start with issuing one of the writes. However, we cannot issue this write because then we won't be able to certify the corresponding step in the promise in semantics, as this write depends on a read event which reads from something which is not issued yet. So we have to start by promising this write. After that, we can either issue this write or cover this read. Let's cover the read. Now, we cannot cover this read, but we can issue this write. Earlier, I showed that the promise in semantics was stepping through this instruction without promising it first. However, it's an equivalent to first promising to write and then to fulfill the promise. So now we can cover this write event, and in promise in semantics, it corresponds to just fulfilling the promise. So now we can cover the read event in the left thread, and the color the last event. So this is how the execution is traversed and simulated by IMM. So wrapping up, in our paper we introduced IMM. We showed correctness of compilation to it and from it. We did that in Coq. Our future work is to prove correctness of compilation from weakest to more memory model, which actually is going to be presented in next talk. This memory model is based on event structures, and it also has some kind of certification, so we hope that we'll be able to use at least some results from promise to IMM proof. And the overall goal of our research here, of this branch, is to verify correctness of compilation for big compilers like concurrent via two weak memory models. There is already a paper on correctness of compilation from concurrent to x86 TSO, but not to more weak memory models. So thank you for your attention.
So I'm not seeing any questions on Slido. Does anyone in the room want to start with a question? Well, I'll get us started then. So actually, I have several, so I can go on. So what do you think it's going to be harder to do in general, to add new programming languages compiling into IMM, or to add new hardware weak memory models compiling out of IMM?
I would say that it's easier to add models on the right-hand side of the picture. However, it also depends on the fact if the new hardware memory models are like these ones, if they are like completely different, or they use some features which are not in IMM yet, then it might be harder. So for example, currently we do not support non-atomic accesses because these memory models, they don't have them in the sense that they are undistinguishable from relaxed accesses. But if, for example, we want to add, let's say, titanium memory model, then we'll have to make some changes in IMM. But speaking about programming language memory models, they usually have have different styles. So, for example, promise in semantics is very different to C11 memory model. That's why it might be harder in general to add them to the picture.
Okay. Does anyone in the room have a question?
Can you tell us a bit more about this IMM model? How come you have found such a generic abstraction of all the weak memory models?
So there is a lot of similarity between memory models, and sorry. Let me answer it offline.
I've got a Slido question here. What about compilation of even more declarative weak memory models like RMC or the Polsberg and Lasani calculus?
Actually, I don't know how to answer to that question, so probably I also will be happy to take it offline.
The questioner will have to seek you out for that one. Any other questions in the room? Okay, I'll ask one more because we have lots of time. So the hardware memory models have different sort of primitive synchronization options, right? Some of them have cases, others of them have load link, store conditional sort of things. So how does that play out in IMM?
In IMM, we use the same approaches in ARM memory model. So we have like read exclusive and write exclusive pairs, and these you can compile whatever, represent whatever you want in terms of read modify writes, like cases or fetch and adds and stuff like that.
Okay. Any more questions?
Where does the Java memory model fit in?
Actually, it's very hard to put Java memory model here because it has some problems, and I'm not sure if we'll be able to add it to the picture.
Anyone else? Okay, in that case, let's thank our speaker again.